t secant theta? Or was it secant squared? Number 7, t secant theta over theta e to the t squared? Is that right? Well, that's a pleasant little expression there, isn't it? How nice. Well, that t secant theta says integration by parts, doesn't it? Sure, don't say yeah. T secant theta?
Oh, no.
No, the t and the secant theta will be totally separated, won't they? These two guys, the t and the e to the t squared, they're going to stay on one side of the equation because they've got t in it. However, the theta and the secant theta will go to the other side of the equation because they have coffee in them. No, I mean theta. Oh, tea and coffee. Pardon me. I had to walk a long way for that one, didn't I? Jeez, thanks for the help. Bless America. So, theta over secant theta? D theta? Well, that doesn't look fun. T over e to the t squared dt. Tell me, is e to the t squared this? Or is e to the t squared this?
That one.
How do you know?
Because first one is 2 times.
The first one is e to the 2t. T. Well, clearly 2t and t squared are different powers. Right? Plug in t equal 3 and you see you have something different there, right? So this is out, this is in, and this is out because it ain't dark enough anymore. Okay, so integral. Well, this one's easy. We'll let u equal t squared, then 1/2 du is equal to t dt. So the integral on the right, no problem. That's going to be the integral of e to the u minus u du. Pardon me?
1/2 on first one.
Oh, thank you. Yeah. What about that side? Thank you. We're not ready to do that side yet, are we? All right. If you try to do integration by parts on theta and secant, you're doomed to failure because that's not the secant. That's 1 over the secant. Better written as cosine. Oh, yeah. Oh, okay. And I'll let u equal theta and dv equal cosine theta d theta. Let's see, so du is d theta, v is sine theta. So this is u times v, theta sine theta, minus the integral of v du, sine theta d theta, all equals minus 1/2 e to the minus u plus an arbitrary constant. Well, maybe we'll wait till the very end to add the arbitrary constant, whatever one that generates. We'll just add to the ones that all the others generated. When we integrate this, we get theta sine theta plus cos theta equals minus 1/2 e to the minus t squared plus an arbitrary constant. Normally you try to solve for, well, not t. T is usually considered to be the dependent variable. So normally you try to solve for theta. Somebody want to tell me why I'm not going to try to solve for theta here? Can't. That's a good reason. If you're good enough to solve that for theta, then congratulations. You have more math ability than you ever wanted.
So why do we choose for the e to the t to the square? Like, why do we choose that one compared to the?
Well, because then you could. How would you? I mean, they could make a definition that works that way. But here's the real reason why we have to do that is exponents work right to left.
Okay.
So this is working on E. However, 2 is working on the t. So I have to start at the rightmost with exponents and work my way over.
Mhm.
So this means e to the t squared. Then e to the t squared means t squared is the power on this. But that has to be done first. That's the
Okay.
rule by which you can figure that out.
Cool.
Just another rule you didn't want to know.
Do you have enough math ability to solve that for theta?
No, sir.
So when do you know when to like, I mean, other than this situation, when do you know? Like,
Oh, you always solve for the variable on top if you can. Question. Alrighty then. So we got to do a few more of these, huh? Number 13. Yeah, that one looks awfully easy. Never mind. 13 does have something different going on. So 13. Somebody read it to me.
Du over dt.
du over dt?
Yeah.
Equal
To
2t
t.
plus equal square t all over to u.
Such that?
U
0. No arbitrary constant on this one, huh? All right. So 2u du is 2t plus secant squared t dt. Hoorah. What easy integration. Gosh, they were nice to us, weren't they?
Yeah.
No. Question?
How do you know that you can multiply the 2 over if it's negative or if that gets like a...
Oh, I could have left that 2 down here, but then I would have had a fraction, and I don't like fractions. What's important is that all the u stuff go with the du and all the t stuff go with the dt. However, I can adjust the constants in whatever way is convenient for me. So there was a 2 over here. So u squared equal t squared plus tan t plus an arbitrary constant.
Does it matter where to put the constant to? Could you put u squared plus c or? Okay.
Yeah, sure. Yeah, because if you don't like this constant here, I'll just subtract it over and write it there.
Okay.
All right, so I need to divide by u if I can. I mean, take square root. But first of all, let's see what c is. How am I going to do that?
X
So
0,
first-
t 0. We can do that. 25.
Oh, sorry, forgot the 2.
So 25 equals.
So c is 25. All right, so u squared equal t squared plus tan t plus 25. Now, in answering one of the recently asked questions, the question was, when do you have to solve for the independent variable? And the answer was, whenever you can. So notice I can take square roots here. However, that square root generates an absolute value on each side. That absolute value is interpreted to mean plus or minus. However, this is not a function. If that's all the better I can write, then I have to leave it at the previous step. Right? It doesn't make really a lot of sense here to solve for u, unless I can get rid of that plus or minus sign.
So u 0.
Why is it 5 0?
Yeah.
When t is 0, u is minus 5.
So it's minus 5 should be negative. Yeah.
Negative.
So it's gonna be negative.
Well, let's see. U is negative, so I think she's right. Isn't that nice? Good thing you're here.
look at the signs, we look at the whatever that such that.
And of course, hopefully back in Calc 1, they kind of told you why that was the case. Back in Calc 1, remember when we integrated like 1 over x squared, when you very, very, very first did antiderivatives, they did not write minus 1 over x plus c, did they? Not the original answer they gave you. What was the first thing they wrote? And then hopefully your teacher explained why they wrote it in 2 pieces, and then said we won't bother to do that anymore.
Maybe absolute value.
Because this is in 2 pieces. Notice it doesn't exist at x equals 0, so really what I was supposed to write, this is minus 1 over x plus c1 when x is positive. But it's minus 1 over x plus a possibly different constant when x is negative. Right, well, that's kind of what they're doing here. I mean, after all, this one is in an infinite number of pieces. The secant squared t has vertical asymptotes everywhere you look. So they have to give us an initial condition in order to eliminate the plus or minus. And in this case, they said, guess what? U is negative. So I guess I don't want the plus. I want the minus.
So the result. So what you were saying there earlier is the result of that integral is always going to have 2 pieces. So it's going to either be.
Well, the result of the indefinite integral, but we made it definite by having that data
Right.
value,
Right.
initial point. Questions? And which one was that? Was that number 7?
Was 13.
Oh, it was 13. Well, we're moving along with great speed now. We've done 2 of them. So, was that fun?
Why'd you put in -5?
Well, because this initial condition, translated into English, says that if t is 0, then u is -5. Questions?
Mm.
47.
No, not quite that far. We're going to skip to 21 now. Yeah, 21 is the essence of this other little
Question mark.
problem that we do, but in differential equations. Y prime is equal to x plus y. Now, the reason that they're using that particular example is not only for simplicity, but remember, we haven't really talked about 9.1 or 9.2. 9.2 is something we're going to discuss right at this moment. You don't have to worry too much about notes because I am not going to assign anything from 9.2. But what you may not realize is that differential equations are what we use to write the equations of rather complicated phenomena. You can use them to describe 3-dimensional solids. You can use them to describe, and this is their more intended use, force fields. Stress on a beam or something is exhibited in differential equations as a force field. And this might very well be a force field that's being applied here. Although what I would do is modify it slightly so it was a little more interesting than just that. But notice what's going on here. If we draw the XY coordinate system, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. What this is telling me is the slope of the tangent line anytime I know the x and y coordinates of the point. So what's the slope of the tangent line at the origin?
0.
Right? Whatever x is, whatever y is, I add them and I get y prime. So I can see that if I'm at the origin, the slope is 0. Well, that means if I'm really close to the origin, the slope is close to 0. So I'm going to approximate the line of force, if you interpret this as a force field, with a real short zero slope line segment. Short because it's only close to the origin that is valid. Tell me, on the other hand, what will the little line of force look like at 1, 1?
2.
Slope of 2. So a slope of 2 at that point would be more like that, so I'm going to draw a little short thing there. What would be the slope here at this point? What would be the direction there? Well, that's 1, 0, so 1. That's a 45-degree angle line. This would be 2, 3, 4. Anyway, you keep doing this, the slopes get a little steeper and a little steep. And the reason we're not doing this is because you really want a computer to draw these. I mean, obviously, you're not seeing much here. So if you look back at 9.2, look at page 634, or better yet, page 633, figure number 7. That is describing something like a force field. What you see there is you could think of that in a number of ways. You could think of that as like wind flowing around an obstacle, or water, right? Turbidity of flow, something like that. And electricity also will follow patterns, but far more chaotic than this. So you could imagine if this is like the flow of water, what you use these little diagrams for is imagine if a cork were dropped into the water. It would follow those lines of force. And they're showing you the different divergent paths depending on where that thing starts. Yes?
Is everything that passes through the y-axis, is it all the
That means that each x is 0. So here y is 1, so the slope is 1. Here y is 2, so the slope is 2, then y is 3, then 4, then 5. So as you get closer and closer to the y-axis, it starts to take you up that way, the flow will. If you were here, it's going to take you up, but over a bit. I'm not going to try to draw it. You have to look at those diagrams in the book. That's why it's always better to have a book, or at least a computer with something you can call up an image. So anyway, that's why they picked that particular example, because it's something that you investigated back in 9.2, I guess. And that's about all we need to say, because it's better done as a computer-generated algorithm, or a computer-generated solution. So all they want me to do here, I forgot what they want me to do. Make a substitution. Notice I cannot separate the variables the way it's written right now. That's dy dx equal x plus y. You can try all day long to separate the variables. It ain't going to work. So the book said, don't try to separate the variables. Let's make a substitution. Let's substitute u for x plus y. Okay, what about dy dx? How in the world do I substitute for that? Let's take a derivative with respect to x. All right, so I get du dx equals 1 plus dy dx. Now I have a substitution for dy dx. Y prime is u prime minus 1. Oh, so let's see, I'm going to replace that with what? U prime minus 1. And I'm going to replace x plus y with
U.
So let's see, that's du dx equal u plus 1. Now I can separate it. Right? Du over u plus 1 equals dx. We can integrate. So I get ln absolute value u plus 1 equals x plus an arbitrary constant. They did not give us any initial conditions here, so I'm not going to be able to find the arbitrary constant. I can, however, substitute in place of u. I can say ln absolute value x plus y plus 1 equals x plus an arbitrary constant. And I can't really get rid of the absolute values because I don't know the restrictions on x and y, so it's about the best I can do there. I could raise both sides as powers of e, but that's not as convenient an expression. Did the book do that? Did they actually solve for y?
I think so.
Okay, let me show you what they're doing then. Somebody, let's make sure they did that, because I don't see any need to confuse the issue if they left it that way. They solved for y? Okay. All right, so let's take this as written. ln absolute value x plus y plus 1 equals x plus c. So to eliminate the ln, actually, let's call this c1. And you'll see why shortly.
Wah, wah, wah. You'll see one, you'll see why shortly.
I don't have to go that far to get a joke. So let's raise both sides as powers of e. Absolute value x plus y plus 1 equals e to the x times e to the c1. So that means that x plus y plus 1 is plus or minus e to the c1 e to the x. Now I'm going to create a new constant. What do you want to call it?
Plus
C.
minus. Oh,
See?
That wasn't there.
okay.
I'm going to let c equal plus or minus e to the c1. So in that case, I can now solve for y. Y is equal to c e to the x minus 1. So, gosh, that was fun. We are having such a good time in this class today. Orthogonal trajectories. Oh, that looks like a good time. Number 30. Anybody asked for? Oh, look, you asked for number 30. How sweet. 30. What do they give us? Y squared equals kx cubed. Well, the first thing we want to note there is that k is y squared over x cubed. So we're going to find dy dx, find its negative reciprocal, and integrate the negative reciprocal to get the orthogonal family. The constant of integration will provide us the parameter for the orthogonal family. So that's why we're going to replace k. We don't want this parameter, that's for this family. The other family, the one we're seeking, the orthogonal trajectory, has to have its own constant of integration, therefore its own parameter. So 2y dy dx is 3kx squared. Everybody okay with that? So dy dx is 3x squared over 2y times k, but what's k?
Y squared.
So dy dx is, yeah, the 3 and the 2 hang around y over x. 3y over 2x. So the slope of the orthogonal family, dy dx orthogonal, and here's the usual expression that you would use for that's the symbol for orthogonality in a linear algebra class. That will be minus 2x over 3y. So, nice catch. I I guess that means 3y dy equals minus 2x dx. Or, I don't know, why don't we write that as 3y dy plus 2x dx equals 0. And now let's integrate.
Wait, why did you separate the K?
All right, I won't.
No, I said, why did you separate the K in the beginning?
Because just to make it easier to substitute in.
Oh, okay.
All right, so I'm going to integrate.
So 3y squared
3 halves y squared
Yeah.
plus
plus x squared.
x squared equals constant. I'm done. Maybe you want to multiply through by 2. So if you do, probably you'd call this C1, just to make it 30. And then multiply through by 2. So 3y squared plus 2x squared equals C, where C
Okay.
is 2 times C1.
Why can't you differentiate when it's the k equals y squared over x squared y? Because wouldn't k equal 0?
Why would k equal 0?
It's a constant, no?
Oh, no. K is a parameter, so it's not equal to 0. It's only equal to 0 sometimes. It's other values at other times.
That was fine. 32.
About 32,
32.
y equal
Minus
1 over.
x plus k.
All right. So that family of curves is a whole bunch of hyperbolas, all with a horizontal asymptote at the x-axis, but the vertical asymptote is at whatever k gives you, right? X equal minus k. So we're going to try to find a family orthogonal to that. Well, what's k equal to? Since xy plus ky equals 1, I guess ky is 1 over xy, and k is 1 over xy minus y. We may want to write that as a fraction. I'll also therefore write that as 1 minus xy over xy. I don't know which of those will be more convenient, but I've got them both right there.
Isn't it 1 minus xy?
1
minus xy. With 1
Oh, what in the world did I write? Goodness gracious sakes alive. Phew. 1 minus xy. It's almost like I knew what I was doing. So that's, well, much easier, isn't it? Oh, well, I'm looking for k, though. Duh. Which, once again, I may want to write that in one of those two ways. All right, so 1 over y minus xy over y. Y prime is minus 1 over x plus k quantity squared. Yeah. So y prime is minus 1 over x plus. How do we want to write k?
Second.
Oh, that second one's nice, isn't it? 1 over y minus x. Hoorah. Right, we like that. So y prime is minus y squared. Yeah?
Yeah.
Is everybody okay with that?
Yes.
Let me see some of the looks I'm getting. So y prime is positive 1 over y squared. Or in other words, dy dx is positive 1 over y squared. So y squared dy equals dx. Let us integrate. So 1/3 y cubed equal x plus c1. And so y cubed is 3x plus 3c1 And y is the cube root of 3x plus c, where c is 3c1.
For the answer, do we have to put like c equals 3c1? 3c.
Yeah, you should. I don't know. I probably won't get too upset as long as it's there somewhere.
And you're not gonna mark down points because of it.
Oh, I'd mark off on you, I'm sure. So, need another short break here? Is that what we need? Let's take another short break. I'll see you back here at 20 till. Then I'm going to talk about the new stuff.